Hello everyone, my name is Vasilis Pettas. I'm a postdoc at DTU Wind Energy, and today I want to present the work we did within the TWAIN project regarding the effects of bat protection strategies on energy production and structural loads of wind farms. This work is done in collaboration with my colleague Tufe from DTU and also Thomas Duke from NG Green and Andreas Vaden and Antonina Vurkabat from Technical University of Munich. So to start with, we all know that bat protection is necessary but can also be costly. Bats are vulnerable to wind turbine collisions, and in order to mitigate the environmental impact, operators try to reduce these effects, but also legally required to meet specific regulations for specific species and different regulations on local and regional level. So most bat protection that exists today reduce energy production and affect the turbine loading potentially due to the more frequent shutdowns. But this is something that is not quantified properly. And the aim of the work we do in the TWAIN project is in order to guide an efficient decision-making on how to approach better the bat protection strategies, to find a way and suggest a method to quantify these trade-offs. Before I continue, I want to explain a bit what are these bat protection strategies that we consider and the most widely used. So first is a static or blanket control, as it's called. In this case, the shutdown of the turbines is triggered by predefined environmental threshold. When these thresholds are met, then the wind turbines are shutting down. These thresholds are derived in the pre-construction phase by experts, where based on the flora and fauna of the region, they can identify variables such as wind speed, temperature, humidity, precipitation, also dates, time of the day, that define these thresholds, which are tunable to different protection levels. So we can have like 90, 99, 100% protection levels, etc. The other approach is a dynamic control, where the shutdowns of the wind turbines are triggered by real-time bat protection using acoustic or image sensors. And then the turbine shut down for a predefined duration when activity is detected only. So this assumes an ideal sensor coverage, and it's considered 100%. This is more novel approach, while the most common approach now in the field is the blanket control. So in the work we are doing within TWAIN, we want to develop a data-driven framework that enables us to evaluate the impact of these bat protection strategies on the wind farm performance. And for this particular study, we used data from an onshore wind farm in France to run a case study and identify these trade-offs. So now I will say a few words about the methodology we used to create this framework. To begin with, I want to show some figures on the correlation of environmental patterns and bat activity, so that we can have a better understanding of the activity patterns of bats. So bats are detected when wind speeds are relatively low. As you see here, this is the distribution of bat activity as measured by a sensor there in the field for 2 years. And we can see that bats mainly appear in wind speeds below 8 meters per second, so closer to the cut-in and in region 2. Then they appear when it's not too cold, so they above 13 or 14 degrees Celsius. And then they are nocturnal birds, so they appear at night and mainly in summer months. So based on this, we can understand how one could derive these environmental thresholds based on more data from multiple years and be able to identify protection levels based on these thresholds. Then I want to talk about the evaluation framework we developed. In a conceptual level, the evaluation framework starts with ambient conditions. So we get wind speed, wind direction, PI, from the site in an ambient level, and also bat activity data. Then, for each time block, we apply this bat control and define the operational state of the turbine, which can be normal production, starting, stopping, or idling. Then we are using the Floris in order, which is a software for identifying the flow of waked fields in a farm, where we feed the environmental conditions, the ambient conditions, and we get the local inflow for each of the turbines. Then we feed that to a trained load surrogate based on our elastic simulation. So at each time step, we can get the damage equivalent loads. So we can loop over a long time series, and then we can accumulate the DLs, all energy production, revenue, or other KPIs over time to give a cumulative value. And thus, we can compare the different cases. A few more details on the modeling. So we use a site-specific calibration from Flores to account for terrain effects and speed-up factors based on the method developed by our colleagues in TWAIN. And then we use the IA 3.4 model for simulations, as we didn't have the actual wind turbine, but it's very close in terms of dimension and capacity with the actual wind farm model. And then we use HOC2 simulations for different cases, normal operation, idling, startup, and shutdown, 10 minutes, in order to create a database for training. Then the surrogate model has as input the rotor effective wind speed, the rotor effective turbulence density, and the operational mode, the 4 modes I mentioned. And the output is the 1 Hertz damage equivalent load and the energy, for example. We tested different methods. Due to the small dataset, it seems that the piecewise spline interpolation behaves better. Here you can see the error between the test set and the trained model, but also we have a neural network model and a Gaussian process regression model that I will not show today. And the BAT control then is applied over time, and we have a state machine which changes the transition of the state of the wind turbine, being either idling, then it starts, then it's in normal operation. So it imitates the normal behavior of the wind turbine. DLs are converted based on minor to damage, and so we can get the cumulative values over time. And the energy production in this case is calculated by Flores. So the case we want to simulate, the first case is the baseline case, where we have no BAT protection strategy, and we want to just running as a reference point in order to compare the next strategies. The first strategy is the static BAT control. We are based on the data we got from the experts from the company. We have the protection levels for 90, 99, and 100% based on temperature, wind speed, and date only. And of course, based on night time. The duration of an event of shutdown is dictated by the environmental condition only in this case. In the second case, we used the data measured with acoustic sensors, which assumes 100% protection, and we only stop the wind turbines when the activity is detected with this 10-minute interval. The stop duration, we decided to test 2 cases, one that is only for 10 minutes stopped when the BAT appears, and when it's considered a 30-minute stop. The environmental data extracted from the SCADA data and patched with ERA 5 from an onshore wind farm in France, and the BAT activity is recorded for 2 years, but the study is for one of the 2 years based on a sonic sensor mounted on one of the turbines. The assumption is that one turbine sensor is considered representative for the entire farm, and that besides BAT control, we don't have other curtailment or shutdowns, for example, for maintenance or for grid curtailment. And that all turbines of the farm start and stop simultaneously. So I want to share some results now, preliminary, which we plan to publish in the next weeks. So here you see for each of the wind turbines, the x-axis is the turbine index, and the y-axis the relative difference to the baseline. So you see the different cases, the static and the dynamic case. What we can see here is that the effect of the duration, of the amount of starts and the duration are kind of competing. So the more starts and stops we have, it increases the loads, but the longer the stops are, this offsets the increase in load. So you can see how, for example, in the flap-wise bending moment loads or fatigue accumulation, we have an increase as we decrease we increase the level of protection from 90, 99 to 100. While the opposite is observed in the tower, and this is the trade-off I mentioned earlier. And also, you can see for the energy production, the difference between the different cases in the lower plot. I will show this cumulative in the next plot. I just wanted to show the differences also between the different turbines due to the wake effects that we have. So now I want to show the condensed results, combining all the wind turbines. So here is again similar plots. You see the different load sensors plus the revenue, plus the energy plot, where we have the relative difference to the baselines, the y-axis, and the scatter you see in the block is the bar plot of the box plot of all the turbines. So all 13 turbines of the wind farm. Looking in the static cases, we see that the effect I mentioned earlier. So in 100%, we have very long stops, which means there is a lower decrease in fatigue or less impact on fatigue when we have increase. While when we go to lower thresholds, this changes due to the more frequent stops. This also, of course, reflects to the energy that you can see in the bottom right, where we start with the 0.4% for static 90 case, while the 99, for example, which is the one used actually now by the industry, is about 1.7% energy loss. And when we go, if we wanted to have 100% protection, we go to a very big penalty on energy, which is about 9%. When we look at the dynamic, we see a different pattern, where in the dynamic case, we have more often starts and stops, which means translates to higher fatigue increases, and but also comes to a lower penalty in energy that you see with a 10-minute stop with a dynamic case, we have about the same energy loss with a static 90 case. While when we increase to 30 minutes the interval, the stop interval, then we have a reduction of about 0.8% in AP, but less effect on the loads. So these trade-offs can guide us to choose which method is more suitable for the site, given the amount of bad activity, the cost of implementation, and other topics. For more details, I will refer you to the paper we're going to publish, where I analyze more this effect and these trade-offs and the amount of start and stops and the trade-offs in loads and revenue. So coming to the conclusion and outlook, I want to say again that we created this data-driven framework that is able to realistically evaluate the effect of back protection strategies, including a wake, aware, and late-out agnostic inflow model combined with a load surrogate model. And regarding the comparison for the dynamic and static cases, we see that static cases, static or blanket control strategies reduce AP more, while the dynamic strategies have a higher impact on loads. For the specific side we investigated in France, we see that both bad protection have a small impact on fatigue load, and probably the decision making will be on the economic level. Although this cannot be generalized, as it depends on the amount of the specific site, the amount of bad activity, and the conditions where the starts and stop happen. For an outlook, what we want to continue doing in the TWAIN project is to investigate the partial shutdown, where multiple sensors exist in the wind farm and only part of it shuts down when bats are detected. And also to evaluate as a next step whether wind farm flow control can offset this impact. So applying some control strategies to increase AP, whether we can somehow offset this reduction we get from applying the bat strategies. So with this, I want to thank everyone, and I'm happy to get questions and discuss more on the topic with you.